So, still going on layers of protection around the central nervous system. We said the bone was the first line of protection, and then we had multiple layers of meninges, the dura mater, which is superficial, and then the arachnoid, and then the pia mater. And then the next line of protection is what we call cerebrospinal fluid. So before I explain the fluid to you, I need to tell you something about the structure of the brain that I didn't know until I was in college. And that is that the central nervous system is hollow. It actually starts out flat during embryonic development and then it closes, but it leaves a hollow in the middle. And the hollow is shaped like this. Okay. Inside the brain, we have what looks like a chicken with a bouffant. Okay. These spaces in the brain are called ventricles, and they're not empty, they're filled with fluid, and they are continuous with the hollow inside the spinal cord that is called the central canal of the spinal cord. So the brain cavities are called ventricles. I lost my ventricle. 1, 2, this is the third ventricle, and this is the fourth ventricle, and we'll talk about the ventricles a bit more in just a few minutes. Actually, probably in a different video. So these two are lateral ventricles, as in lateral, okay? The one that's in the middle right here is the third ventricle. It looks like a chicken head. The fourth ventricle is right here between the cerebellum and the brainstem, and then the central canal of the spinal cord. It's continuous with those. Each of the ventricles are lined with glial cells, neuroglial cells, that are called ependymal cells, and we talked about them in the last set of notes. Where are you, ependymal cells? So do you remember seeing these in the last set of notes and me trying to explain that the brain was hollow and there were ventricles in the brain? So these ependymal cells are going to be responsible for making cerebrospinal fluid. And what they're really going to do is they're going to kind of pull fluid, solutes, nutrients, ions from the bloodstream, and they're going to pull all of the best stuff, and then they're going to dump it into the ventricles of the brain. So let me show you a couple of different ways of looking at that. So these glial cells, so if this portion right here was a ventricle, okay, and this is a coronal section of the brain, and you're actually seeing some ventricles right there. So if this was a ventricle, then these ependymal cells will snuggle up to a capillary in the brain. And what they will do is they will pull all of the juiciest stuff out of the blood plasma, and they will make it basically into cerebrospinal fluid, which is kind of like blood plasma minus clotting proteins plus a whole bunch of ions that you need for nervous system. And they're going to dump it into the ventricles of the brain. And then we'll talk about how it actually circulates in just a second. So this is in the ventricle of the brain, the cerebrospinal fluid. So let's go back to this one for just a second. Okay, so what do you call ependymal cells plus the choroid plexus, or plus the capillary that they take the stuff from? It's this little red boogery looking thing called a choroid plexus. So the ependymal cells in the choroid plexus. These two things together are going to make cerebrospinal fluid. And then the cerebrospinal fluid is going to circulate. So stick with me for just a second and we'll go through this several different times. Remember, these two ventricles are the lateral ventricles. They're also called 1 and 2. Here's the chicken head from an anterior view. That's 3. Here's number 4, okay? And then here's the central canal of the spinal cord. So I want you to see what the cerebrospinal fluid is going to do. It needs to eventually make it out into the subarachnoid space, but it's going to have to circulate inside the brain first. So we're going to go through this a couple of different ways. So all of the cerebrospinal fluid that's made in the lateral ventricles, in the choroid plexus of the lateral ventricles, the little red booger looking things on the wall, which is represented right here. Now this is a mid-sagittal section, so they're trying to show you that that's like behind the picture. So in the choroid plexus of the lateral ventricles 1 and 2, you are going to make cerebrospinal fluid. But in order for that stuff to get out of the brain, it's going to have to go into 3, okay? This is ventricle number 3. Do you see the chicken head? Now the tissue is not called the ventricle, it's the space that's called the ventricle. So this chicken head corresponds to this chicken head, okay? So this is ventricle number 3. And then what's going to happen is it's going to have to go down this little path right here. That's called an aqueduct. I'll tell you the specific name of the aqueduct. And then, so 1, 2, and 3, all of the cerebrospinal fluid that was made there has to go down the aqueduct, gather some more cerebrospinal fluid made in number 4. Again, number 4 looks like this from the side and this from an anterior view. It's between the cerebellum and the brainstem. And then whatever you gathered from 1, 2, 3 in the middle, 4 down at the base of the brain, all of that can either move into the central canal of the spinal cord or go into this gray space. And that gray space is the subarachnoid space. Okay, let's see if this animation will work. Oops, that one's not working. I'll have to find it. Okay, so most of the cerebrospinal fluid is actually going to go out these little holes. And these little holes, there's a median aperture in the middle. Aperture means opening or window. And there are, so a median aperture in the middle right there, and there are lateral apertures on the side, and you can kind of see these apertures. And what those do is they reach up from inside the brain into the subarachnoid space to allow for the cerebrospinal fluid that was made inside the brain to get outside the brain, because it's the same fluid that is actually going to circulate both places. So this is only showing the median aperture because it's a mid-sagittal section. It's not showing you the lateral apertures. Okay, so let's talk about what's in this fluid, this cerebrospinal fluid, for just a second. In a healthy person, there's generally only about 500 milliliters, a half a cup of cerebrospinal fluid at any given time. That can't vary very much, or else you're going to have the worst headaches in the world and some other potential problems. And what's in it is like a whole bunch of glucose, because the brain really likes glucose, oxygen, vitamins, necessary ions like sodium and potassium and calcium and chloride. And so it's circulating both inside the brain and around the outside of the brain. And it's both chemically protective because it's got all that good stuff in it, but it's also physically protective because it cushions the brain from jolts. So like every time you get hit in the head, you don't get a concussion, in part because it's like sitting in soup, which is the cerebrospinal fluid. So I want to go through cerebrospinal fluid circulation one more time. And I think I'll have an animation I can link for you. I just can't remember where it is. So cerebrospinal fluid circulation. So this is the same thing that I went through, only it's listed as a flow chart, and it's got a tiny bit more information on it. And it goes with this picture as well. So where is cerebrospinal fluid made? Where does it circulate? How does it get out of the brain? So let's tell the whole story, both with the picture and with this. Okay, so the place that it's made is by the ependymal cells in the choroid plexus, okay? Ependymal cells and choroid plexus. Those are the little pink booger looking things on the wall, and it's a combination of ependymal cells and capillaries. So you're going to make it first in the lateral ventricles, 1 and 2. Which you can't see on this picture because it's a mid-sagittal section. And then from the lateral ventricles, you're going to go to the third ventricle and make more with the ependymal cells and the choroid plexus in the third ventricle. Then I'm going to go down this aqueduct. Now, a lot of people call this the cerebral aqueduct, and that's what it's called right here, and I'll let you call it that, but that's not its real name. So the cerebral aqueduct right here. And then from 1, 2, 3, go down the cerebral aqueduct, and then they meet up and gather more in the fourth ventricle. More ependymal cells and choroid plexus make more cerebrospinal fluid. And then most of it actually leaves out the median and lateral apertures. Okay, some of it goes down the central canal of the spinal cord, and that's got fluid in it as well. But most of it leaves out the median and lateral apertures, and then it goes into the subarachnoid space. But now we have to put the story all together, because after it gets into the subarachnoid space, it circulates around the outside of the brain, but we never stop making it. So you always have to get rid of the old stuff so you've got room to make more. So I'll talk about this part in just a second. How do you get rid of most of it? Remember that I have these one-way valves called arachnoid villi. Villus is singular. And those are one-way valves that will actually allow cerebrospinal fluid to get dumped back into the bloodstream, which is where you took it from in the first place. And really where back into the bloodstream? Into those dural venous sinuses. This one is the superior sagittal sinus, but there are others, straight sinus, transverse sinus, all of those. Okay, and then went from the bloodstream where I took it all the way back into the bloodstream. And then this was just found a few years ago, and it's not super important, but it is kind of interesting. I've got nerves coming and going from the brain and the spinal cord, and they did figure out that some of the cerebrospinal fluid actually leaks out down those nerves. Not very much, but at least a little bit. So I don't usually ask you about that part. These I definitely do. Okay, so there is no way to stop making cerebrospinal fluid once you've started making it. So you just make it all the time. And like I said, it's really important to actually get it out after you've started making it. So let me show you what happens if it gets stuck in there. So again, this is a mid-sagittal section showing you how big those lateral ventricles usually are. They're not usually huge when you look through them, but if something gets stuck in here, quite often, not always, it will get stuck in the cerebral aqueduct. And what happens if you can't get the fluid out from the inside of the brain? Well, you don't stop making it. You start putting pressure on the brain from the inside out, and you can actually increase the size of the fluid cavities in the brain. And it's not better to have more fluid in the brain. It's actually going to push your cerebrum up against the bone, and you can make these ventricles enormous, and this is going to cause brain damage. When this occurs in a developing fetus, it can cause what's called hydrocephalus, because the pressure from the inside of the brain pushes the brain up against the skull, and because the skull is still forming, of course, the skull will increase in size. This is called hydrocephalus, and this is another baby with hydrocephalus. This is not good news for these babies. That level of severe hydrocephalus, either of these three pictures, is going to cause permanent neurodevelopment problems. These babies are going to have a tremendous amount of neurodevelopment problems, and sometimes it's even life-threatening when it's that severe. So the fluid that's built up in the skull is called hydrocephalus, which means water on the head or water on the brain. Now, if this occurs in not a developing fetus, but an adult, the skull is already, the sutures are already sealed. So the skull is not going to increase in size. But if it occurs after the sutures have healed, what's going to happen is you are actually going to have to put a shunt in past the site of blockage, and then drain the excess cerebrospinal fluid either into the peritoneal cavity or into a blood vessel, because the pressure will cause brain damage if you don't shunt the cerebrospinal fluid, because there's no way to stop making it. Okay, so that's cerebrospinal fluid circulation.
Cerebrospinal fluid, or CSF, circulates freely through the ventricles of the brain, the central canal of the spinal cord, and the subarachnoid space. It is produced in each of the 4 ventricles by the choroid plexus, a structure that consists of specialized ependymal cells, their associated blood vessels, and connective tissues. The endothelial cells of blood vessels within the choroid plexus and ependymal cells are joined by tight junctions and collectively form the blood-CSF barrier, a portion of the blood-brain barrier. The selective permeability of this barrier controls what molecules are able to reach the cells of the brain. We can trace the flow of CSF starting in the lateral ventricles. From the lateral ventricles, CSF flows through the interventricular foramina to the 3rd ventricle. From here, the CSF enters the cerebral aqueduct and travels to the 4th ventricle. Once in the 4th ventricle, the fluid enters the subarachnoid space around the brain and spinal cord by either passing through the 2 lateral apertures in the walls of the 4th ventricle or through the single median aperture located in the roof of the 4th ventricle. A portion of the CSF also enters the central canal of the spinal cord. Accumulations of arachnoid villi, called arachnoid granulations, project into a venous channel within the dura mater known as the superior sagittal sinus. CSF is recycled into the venous part of the bloodstream at the arachnoid granulations. The turnover rate for CSF, from its production at the choroid plexus to its reabsorption into the superior sagittal sinus, is approximately 0.4 milliliters per minute.